Hi everyone, this is going to be a review of Mergesort. So let's get started by building some intuition for what the algorithm is doing, okay? So I like to imagine Mergesort is that we take this initial array and then we break it up into a bunch of one element arrays, okay? Or we break it up into a bunch of like 0, 1 length arrays. Then all Mergesort does is that it looks at neighboring arrays and it merges those neighboring arrays together, okay? So what we can see here is that we take all of these neighboring arrays and we merge them together and we get the following 4 two-element arrays. Now we're going to repeat this process. We're going to say, hey, you neighbors, merge together into one sorted array. In the same fashion, we'll take these two neighbors and merge them together. So this merging step that I keep mentioning actually runs in linear time because we know that both of these two arrays are in sorted order. So all that we really do when we merge these two sorted arrays into one fully sorted array is that we keep comparing the first element, and whichever one is smaller, we move it here and then we remove that element, and then this one becomes the new first, right? So we can see when we merge these two, 2 will first go, then 6 and 3 get compared, and then 3 goes, then 5 and 6 get compared, and then 5 goes, and then finally 6 fills in that last spot. Okay, so this is the idea of merge sort, where we have a bunch of people start off, I don't know, by themselves, then we keep merging neighbors together. Okay, well, let's kind of dive through this in terms of code. And we will see that this intuitive way that I approached it didn't have the entire picture, but it was very close. Okay, so when we think about the pseudocode for merge sort, all that we're doing here is we have some sort of base case. Okay, this is our base case. And it's saying that if the list I'm given is of length 0 or 1, we know it's already sorted. So let's just return the list. Simple base case. Okay, now what we're going to do is we're going to break our list into two halves, a left half and a right half. We're going to call merge sort on the left half. We're going to call merge sort on the right half. And we're going to assume merge sort works, right? Take that recursive leap of faith. Now we're going to say A is the sorted left half, B is the sorted right half. All that we have to do now is merge A and B together, and we get our final sorted array. So this may seem a bit skeptical to you all, saying like, how can we just trust recursion to work? So let's actually see merge sort in action here, right? So what we're going to do is let's move this down a little bit. Okay. Now let's paste this back in. Okay. So I have this little visual here. And suppose that we call merge sort, which I will represent as MS, on this entire array. What's going to happen, right, because of our pseudocode, is that we call merge sort on the left half and we call merge sort on the right half. Accordingly, we're going to issue two recursive calls, right? So the first recursive call is on 7194. The second recursive call is on 3562. And we repeat this process. So we have these two recursive calls in the beginning, and then we keep issuing more recursive calls as we keep breaking up that initial array into little pieces. Okay. Eventually, we call merge sort in this example on a bunch of one element arrays. And what's going to happen here is that we will hit our base case, and we're going to say the list is of length 1. Let's return the list since it's in sorted order. So what's going to happen here is, at this point, each of these calls to merge sort returns the following single element lists. Okay? So just to recap, all we've done so far is we've taken the initial call to merge sort, and we've looked at every single recursive call that follows, right? We can kind of imagine this as all of the recursive calls, right? Because in merge sort, we first have a bunch of recursive calls, then we take the information from the recursive calls, and we kind of build the sorted list together with merge. So now what we do, once we have all of these single element arrays, is the magic of merging comes in, right? So far, in terms of pseudocode, all we've done is we've executed these 2 lines of code, right? So what we need to do now is actually execute the merging in each of these function calls. So what we will do is we will continually call merge, which I will represent as this green line, on all of these pairs, right? And then what we'll notice is that finally we will get an array in sorted order, okay? So this is the exact way that merge sort works. Just to recap, what we're doing in merge sort is we have an array, right, that we want to sort. So we take this array and then we break it up into a left half and a right half. We call merge sort on the left and right halves. And if we look at all of the recursive calls that follow, it kind of looks like this following diagram, right? So looking at this diagram, we'll notice that once we get to the bottom where we have our base case, we're going to kind of build our way back up these recursive calls by merging neighboring lists together. Okay, so that is the essence of how merge sort works. So let's move on to its runtime. Okay, so what is the runtime of merge sort? Well, as my drawing shows, it's n log n, but let's see why this is the case. Okay, so over here we have the pseudocode for merge sort. Let's kind of try to draw a recursive tree corresponding to the recursive calls. So the first time I call my function, let's assume the length of the list is n, and we're going to put that here, okay? In my drawing, I'm just going to label this as the length of list passed in, okay? And then inside of this circle, we're going to put in the work done in that function call, which in this case, what we'll notice is that every time we call merge sort, we really have 3 things that happen. We have 2 recursive calls to merge sort, and then we call merge on A and B. Well, how long does merge take? Merge takes linear time, okay? So what we'll notice is that the only work that we do in this function is in merging. And merge is a linear time operation, so what we can say is that every time we call merge sort, the amount of work we're doing for that function call is n work, and we issue 2 recursive calls, okay? So we have 2 recursive calls here. Both are going to have input size n over 2, okay? Then what we're going to notice is that looking at these recursive calls, they will also perform work that is entirely composed of merging, right? And we know merge takes linear time, so we can say the work done in each of these function calls is n over 2, and then they each issue 2 more recursive calls. So let's just draw out that last 3rd layer, and then I think we'll figure out what the runtime is, okay? I apologize for the slightly uneven spacing. I will do my best. So we have 2 more recursive calls here, and then the input size for all of these recursive calls on this new layer is n over 4. And we know that the amount of work we do is the exact same as the size of the input in this example, so we know that each node on that 3rd layer is doing n over 4 work. So the next step in finding the runtime is we want to figure out the work per level, okay? How we do that is we can kind of look at, change the color. We can kind of look at each of these levels and then sum up the total amount of work that we do in all of the nodes. So at the top level, we do n work because we only look at this node right here. At the next level, we also do n work because we're summing up n over 2 and n over 2. Right? On the next level, we also do n work because we're summing up all of these. So what we'll notice is that at each level of the tree, we're doing n work, right? So how many levels are there in this tree? Well, the height of this tree, let's say the height is log n. So the total amount of work we're doing is the work per level times the height, right? So we see the total work, aka the runtime, is going to come out to n log n, which is how we get the best and worst case here. Okay. Well, with that in mind, Let's move on to why would we ever use merge sort? And what we'll notice is that from our calculations, merge sort has a pretty good worst case bound, and log n is equal to heap sort for the best sorting algorithm we've seen so far. And another perk for merge sort is that it's a stable sorting algorithm, right? So why exactly is it stable? Well, we'll explore that in the following question. But yeah, that's one benefit. And the last benefit that I've written here, there are other benefits, is that it's good with linked lists. We can kind of see that like all of these operations would work pretty well on a linked list. So moving on to our understanding question, since merge sort is stable, how can we change merge sort with as little work as possible to lose stability? So when I say lose stability, what I mean is that now merge sort isn't stable. So pause the video, try to think about this question. It's a little silly, but I think it's a good understanding check. And I'll be going over it in a couple seconds. So I'll be going over it right now. And all we have to do to change or to lose stability is we're going to modify the merge subroutine. So let's first try to understand, why is merge sort stable, okay? Well, suppose that let's say we have some big array. And then in this big array, I have two elements that are the same, which we will denote 1a and 1b, okay? At some point, we're going to be merging the array that 1a contain or is part of with the array that 1b is part of, right? So we'll say one merge of like 1a with the array that 1b is part of. When we do this, we will compare 1a to 1b, right? So which one do we want to come first in the answer array to merge? Well, we want 1a to come first if we want to keep stability, because 1a comes before 1b in the original array. So how merge addresses that, it says we have a and b here, right? If the head, this is Wikipedia, if the head of a, head corresponds to the first element in a, is less than or equal to the head of b, then we choose a over b, right? This less than or equal to is how we break ties. So what we'll notice is that when these two elements are equal, we choose 1a and we keep stability. So in order to lose stability, all we have to say is right here, if the head of a is strictly less than the head of b, now what's going to happen is that we will always choose 1b before 1a, and now our algorithm isn't stable, right? So that is all for this walkthrough. I hope you all found it helpful. And yeah, have a good rest of the day.